Hello everybody. Today we shall discuss about another analysis called the phasor analysis. We have been seeing all along that there are lots of different analysis in different domains that we have been applying for the understanding of the circuits. We initially obtained the state equations, studied the dynamic behavior of the RL, RC, RLC circuits. We saw how we go about obtaining information about the circuit in three major domains, which is the time domain, the frequency domain and the pole zero domain. And we saw how we can extract from the state equation the transfer function and see how the picture evolves in the pole zero domain and so on. So, there is one more analysis that you need to become familiar with before we start discussing the other major components in electrical circuits and networks, which is the transformers, the induction motors, the DC motors and the others. And this analysis, which is called the vector analysis or the phasor analysis, gives you information about the relative phase differences between the various waveforms in the circuit. So, you could have the voltages, currents in various branches. How are these various currents and voltages displaced with respect to each other in a phase shift manner, that is the phase shift between the two waveforms. And then what is the active component of the power, what is the reactive component of the power, all this information can be obtained from the phasor analysis. There is also another important thing that can be obtained from the phasor analysis, which is the power factor for the sinusoidal. Of course, all the analysis will be performed with sinusoidal wave shapes. The importance of the power factor will be discussed later in a later session, but however, that is also an important feature of a particular circuit, which also will be obtained from phasor analysis. So, phasor analysis is pretty important analysis and useful analysis for you to understand and use it in the circuits, especially for circuits with sinusoidal excitation. So, all these applications, all these analysis, that is this phasor analysis, the sinusoidal steady state analysis are applicable for sinusoidal excitation. However, the transfer function and the state space analysis are applicable for any excitation. So, let us discuss today the concepts of phasor analysis. So, in the phasor analysis, a sine wave is represented as a space phasor or a space vector. We saw earlier that a sine wave can be represented in space by a vector. So, let me draw two axes. Now, let us say this is a spatial coordinate system. We will call this the alpha axis and the beta axis. So, the alpha and the beta axis are always orthogonal, which means 90 degrees. And then we have, of course, the temporal coordinate system, which is with respect to time. This is the temporal coordinate system, which is with respect to time. Now, we have to map the temporal wave shape, that is the time wave shape, the wave shape that is evolving with time, into the spatial coordinates, and then we obtain the space vectors or the space phasors. So, let us take a sine wave. So, we have a sine wave here. Now, this sine wave starts with time equal to 0, this is time equal to t by 2, and this is t, where frequency f is equal to 1 by t. Or if it is in terms of angle, we say that one whole period is completed from 0 to t, and then again it repeats for every period, which means this could be considered as 0 degrees, this is pi, that is in radians. Let us fix it all in radians. So, 0 radians, pi radians, 2 pi radians, that is this point here. So, of course, this point, the peak, where the peak occurs will be pi by 2 radians. Now, and this would be 3 pi by 2. Now, equivalently, let us take a vector. Now, this is a vector. Let us say this is a spatial vector in space. It could be a pole, okay? I mean a stick. Let us create some space here. Let me erase out this. Now, this stick has a, this vector has an amplitude V m, that is its length. It is anchored at this point, and this is same as the peak of the sine wave V m in the wave shape in the temporal coordinate system. So, now this V m is made to rotate, being anchored at the center here, and it starts rotating like this and completes one circle for one period. That is, it starts from 0, goes through a 90 degree shift. So, there would be a pi by 2 if the vector was at this point, then it is 3 by 2, 3 pi by 2, sorry, it is pi, and then a vector at this point which is 3 pi by 2, and then you have 2 pi. It comes to 2 pi. So, a vector which rotates like that completes one complete circle is equivalent to a sine wave which has completed one period. And amplitude wise, you should see that vector at this position at that corresponding angle shift theta will have a projected amplitude on the vertical axis at exactly the corresponding angle theta from the 0 or the reference. So, likewise, every point on the circle will map onto points on this sinusoid. So, when it comes back again to 2 pi, this would have come back to 0, the amplitude would have come back to 0. So, at every position of the vector, you take the projection of the tip of that vector onto the vertical axis, and then take the angle, and then take the corresponding angle on the time axis, and then place a point there. So, you will see a sine wave evolving. So, which means this sine wave is equivalent to this vector of this amplitude rotating at that frequency, that is rotating at a frequency of f or 2 pi f or omega, which is equal to 2 pi f at the radian frequency of omega. So, now that we have an idea that a sinusoidal wave shape can be represented in the spatial coordinates by a single vector. At any given point of time, the vector is in that spatial coordinates anchored at the center at any position angle corresponding to the time, which is 0 to 2 pi in the case of the spatial coordinate system. Now, if I am having in the temporal coordinate system one waveform which is shown in the blue line like that, and let there be another waveform, and let me put it phase shifted like that, and let me draw the sine wave, and the amplitude is also different. Sorry, goes like that and here, and this can be extended like that. So, this is another. So, this is, let me call this one as A, and let us call this as a waveform B. Now, let us try to project this onto the spatial coordinate system, that is the alpha and the beta axis system. So, this is the alpha axis, this is the beta axis, orthogonal axis, this is the center 0. Now, these two sinusoids are having two different amplitudes and different phases. They start with different phases. So, how do you represent them? So, let us take first the blue waveform. Blue waveform has an amplitude, let us say A m, and it is starting with 0. This is this one, and this has amplitude of A m, and let it reflect onto the, let it be projected onto the vertical axis. So, we see the peak to peak amplitude here, and the red has a peak to peak amplitude of this magnitude as shown here, like this. So, which means the blue equivalent space vector will inscribe a circle within this, and the red waveform will inscribe a circle within this. Okay. So, the blue waveform is starting from 0, because this is starting from 0. So, the projection of this vector at time t equal to 0 is 0. So, we could take the alpha axis the reference axis. Now, the red waveform is starting with some value which is not 0 at time t equal to 0. So, relatively the position of, so this is the B waveform, that is the B space vector and the blue space vector. So, the blue space vector and the red space vector are displaced like that. So, this would be A and this would be B. Now, this unit as a whole together, they start rotating and they complete a cycle, because this together at every point of time preserving the same phase difference between the blue space vector and the red space vector, you get. Or in other words, if we have a space vector like blue and the space vector like this red as shown here with the space difference, and then if they rotate at some given frequency, both rotate at the same frequency, then on projecting onto the temporal coordinate system, they will evolve into the sine wave as shown here, where the red sine wave is lagging the blue sine wave. So, which means the red phasor here is lagging the blue phasor. This is the meaning of this particular thing. Now, how do we apply it for the case of the circuits? So, let us take now only the alpha and the beta axis. So, let me take the beta axis and we have the alpha axis. So, this is the alpha axis and the beta axis. Normally, it is good to have a reference. So, the starting reference is something that we apply. So, we know that we apply the excitation voltage, which is sine wave, the input voltage. So, it is a good starting point to have a reference. So, let us say that we have along this alpha axis, we say that V I or the input or the V in, this is the space phasor or the phasor of the input wave shape or the input waveform. Now, this is going to be rotating with an amplitude Vm, whatever it is, and it is going to rotate with a frequency of omega radians per second. And this, when reflected onto the temporal axis, will result in a sine wave, which is going to start from 0 like that. When this completes one complete circle, you will see a sine wave having a word. Now, the currents, I could probably have a current which is in phase. So, this is my I phasor or the vector, or one could have a current, let me call this one as I 1, or a current which is lagging, let us call this I 2, or a current which is leading, let us call this I 3. So, this current I 1 could be in phase with the applied voltage, which is this, or it could be lagging by some angle theta 1, or it could be leading by some angle theta 2. So, if it was I 1, you would see the current waveform like this, that is I 1. If it was I 2, I 2 is lagging V in. So, you will see that it lags like that. This would be I 2. If it were I3, it is leading. So, therefore, we will see like that. This would, it implies that this is starting somewhere there. This would be I3. So, this way you could have these three positions, that is, you could have a in phase that is, you could have a current which is in phase with V in, along V in, or you could have a current which is lagging V in, that is the applied voltage, or you could have a current which is leading the applied voltage V in. So, these are the three possibilities that you could obtain. But how do these three possibilities come? So, if I take for example, a purely resistive circuit. So, you have, let us say, a voltage source V I, this is V in, okay, and then this is a resistance R. Then you have I, and there is a current which is flowing through this one, and we will call that one as I. Then I is equal to V in by R. R is just a constant and is an algebraic constant. There is no phase associated with it, there is no phase shift associated with this one, and therefore, I will be having the same phase whatever it was with V in, because I is a variable, V in is a variable, R is a constant. So, therefore, instant by instant, if I had V in which was like that, with respect to time, that is the temporal coordinates, then I would be in phase with V only this peak, and if this peak were V m, this would be V m by R. And this is the I waveform, this is the V waveform. Now, if I project this into the spatial coordinates, the alpha beta coordinates, let me start by taking V in as my reference. So, if V in is something vector with an amplitude V m, then another vector, we will call that one as I vector, is having an amplitude V m by R, and that is also in phase, because both are starting from 0, that is also in phase with some value, and that would be the I vector. So, if you see, I have one vector with amplitude V m, and I have another vector with amplitude V m by R. Now, this whole combination is rotating with frequency omega as determined by the frequency here, t is equal to 1 by f, and omega is equal to 2 pi f, which is equal to 2 pi by t, with that angular frequency, the radiant frequency. So, this whole set is rotating at that frequency, but we want to know the relative measures or the relative differences between the different at the various phasors. So, therefore, we take a picture at an instant. So, this is that picture at an instant, at any one particular instant, and it gives a picture of the current and the voltage phasors relative to each other. Of course, in this case it is in phase. Now, if you take the example of the capacitance connected across the AC source V in C. Now, there is a current here I flowing. This is going to offer, capacitance is going to offer an impedance capacitive reactance which is J minus J into Xc, minus J into Xc. This of course has a frequency component, that is nothing but 1 by omega c. So, what is I? So, I is a complex quantity which is V in by the reactance which is X c. But there is this J operator which indicates that this is going to introduce a phase shift of 90 degrees, and because it is minus, there is going to be a minus 90 degrees phase shift to the voltages that is going to come across C. So, which means the voltage that is going to come across C, which is same as V n, is going to be minus 90 degrees behind the current vector or the current waveform, which means current is leading the voltage. Let us just have a look at the simple simulation of this. So, what I will use PSpice for simulating this. We will have a reference ground node, we will call that one as 0, there is one node 1 here. So, V in is connected between 1 and 0, C is connected between 1 and 0, and let us give a sine wave here of 50 hertz and then simulate and see what happens. So, going to this PSpice editor, we have here Vi, V input, between node 1 and 0, a sine wave of source, 0 DC offset, 10 volts amplitude, 50 hertz, 0 rise time, 0 fall time, and no phase shift. And then a capacitance is also connected between 1 and 0, node 1 and 0, and it has a value of 1000 microfarad, 1000 E minus 6. And let us do a transition analysis from with a step of maximum step of 1 millisecond, 20 millisecond is the maximum time, that is one period, and then let us probe and see the waveforms how they look like. So, let us simulate this circuit in SPICE. So, on simulating you see the IC and the voltage across this one. So, the red one is the voltage that you are applying, you see that is starting from 0, and the current, which is the current through the capacitance, is already at the positive peak, and then it goes down, cuts 0 at 90 degrees corresponding to the voltage, and then becomes again 0, that is negative peak when the voltage is 0, and so on. So, you see that there is a 90 degrees phase shift between the current and the voltage. So, if you see the voltage is 0, current is positive maximum, which means the current is leading the voltage. So, if you go back to our notes here, so we have the temporal wave shape in this form T. So, we saw that the voltage is our reference of course, and therefore, we are writing the voltage waveform like that. So, when the voltage was at 0, the current was already at its peak, and then it became 0 when the voltage was So, it goes like that. Like this. So, this is your I, this is your V in. So, now let us see how it gets projected onto the alpha beta axis, alpha beta axis. So, what is our reference? Reference is the input voltage. It is starting at 0. It has an amplitude Vm. So, this is our V in. Now, the other phasor is starting, this is starting at this point. What is the angle? The angle between these two is 90 degrees, 90 degrees leading. So, the current is leading 90 degrees. Now, this whole unit is rotating with a frequency omega. Now, you should see that as it is rotating, you see that this will now decrease, the current is decreasing, because when it goes on this side, the projection decreases, and as it comes to this point, this is 0 as far the current is concerned, and that is at maximum 90 degrees. So, this will be the I. So, if you see relative to the voltage V in, I now have an I which is leading the input voltage by 90 degrees, by 90 degrees. This would be the phasor relationship between the voltage and the current in a capacitive, pure capacitive circuit like this. How does it look like for the inductive? Now, in the case of the inductive circuit, we have the source and we have the inductor. We have the inductor L, we have the source V in, and this gives an inductive reactance or impedance which is JXL. XL is omega into L. Now, how does this give you the current waveform in relationship to the voltage waveform? So, in this case, when a voltage is applied, because of the inductance effect, it is not going to allow immediate change in the current. So, the current is going to be slower in rising when the voltage is rising. So, which means the current will lag the applied voltage. And also, if you see from the JXL term, the voltage across the inductance is going to be multiplied by J, that is JXL into I, that is the voltage across the inductance, which is the applied voltage. So, which means there is going to be a rotation of 90 degrees for the voltage. So, which means that the current, the voltage is going to be ahead by 90 degrees with respect to the current, or in other words, the current is lagging the voltage. So, this is what would happen in the case of the inductive circuit. Let us look at the temporal wave shape pattern of the voltage and the current for this pure inductive circuit. So, the voltage is considered as the reference waveform starting from 0 like that, and this is the 90 degrees point, or shall we say pi by 2 point. Then the current waveform is going to lag the voltage by 90 degrees. So, it will reach a peak when the voltage is 0, then starts coming down, so on, like that. So, which means, and it starts coming like that. So, this is the current waveform I, and this is the voltage waveform V in. Now, let us look at how it looks like in the spatial coordinate system, the alpha beta coordinate system. So, again we are taking V in as the reference starting from 0, let that be this vector, this is the V in vector. Now, the current, it is starting at the peak, minus peak, and with a phase shift of 90 degrees. So, this is the current vector. Now, this too as a set rotates with a frequency of omega, which is 2 pi by t or 2 pi f radians per second. Now, you see here the current is lagging the voltage vector. So, therefore, you say that the current lags the voltage, and this is a lag circuit. So, we come to three important types of vectors, vector combinations. So, I have the voltage vector V in and the current vector which is in phase, is the I, or I have the voltage vector V in and the current vector which is, let us say, leading the voltage vector by 90 degrees, or I have the third option we saw in an inductive circuit for a voltage vector as shown, the current vector is lagging by 90 degrees. So, this is for a pure resistive circuit. This is a pure capacitive circuit, and this is a pure inductive circuit. However, in actual practice and real circuits, we will not see pure resistive or pure capacitive or only pure inductive circuits. It will generally be a mix of these. So, we do not get the current leading or lagging by exactly 90 degrees. So, it will be somewhere in between depending upon the values of the resistance, the values of the capacitance, values of the inductance and so on. Okay. Now, let us take the RC circuit which we have been seeing for quite some time, and we are now quite familiar with this circuit RC. This is our RC circuit, RC, this is V in. So, V in is the voltage that we are going to use as the reference. Just by looking at this, we see that there is of course going to be a current which is flowing through this, and that we call I. If there had been no R, it is going to be a pure 90 degrees lead. The current is going to lead the voltage by 90 degrees. R does not introduce any phase shift. So, which means by using an RC, it is going to be somewhere between 0 and 90 degrees lead, depending upon the value of the R and C's. This of course is going to give you a capacitive reactance JXC minus JXC. So, now let us draw here directly the spatial coordinate system, the alpha beta. So, this is directly the spatial coordinate system. Now, here let us take our reference vector as V in. So, V in is a reference vector. Now, I know that the current here is going to lead the voltage by what amount, of course, we could see later. Therefore, a current is going to be somewhere in this, let us say, direction, because it is leading. The current I is leading the voltage by some angle theta. This implies that there are two components to this current. There is one component which is in phase. So, we call that one as, let us say, I alpha, and there is another component which is 90 degrees phase shifted with respect to V in, and we call that one, let us say, I beta. So, I alpha is the in phase component of V in, I beta is the component of the current which is 90 degrees or orthogonal to V in. Now, this whole unit is rotating at frequency omega, and this is a picture at an instant of time when V in is equal to 0. That is, the V in projection is equal to 0 on the temporal axis. So, given this situation here, the in phase component when multiplied by R is going to give you I alpha into R, which is the voltage across R, because the I beta is due to the capacitive portion, which is causing this one. So, I alpha into R is the voltage portion which is going to be in phase like that, and I beta which is due to the capacitive reactance, and this is the resultant current due to the in phase component of the current and the out of phase component of the current. So, this is how the vector diagram would look like for an RC circuit. Now, there is an angle theta here. What is the phase difference? What is the phase shift? Now, the voltage across the capacitance is minus JXC, which means whatever may be the current that is flowing through this, current vector which is flowing through this, gets multiplied by XC and gets rotated minus 90 degrees. So, let us say we have this current which is flowing through XC, I is flowing through XC, that now gets multiplied by XC and then gets rotated 90 degrees, and let us say I put it in a different color, gets rotated 90 degrees and comes like that. So, which means this is 90 degrees, and this amplitude would be x c into I, and whatever I is flowing into R will be along that. So, the voltages wise we have, let us say if R was unity, it is I into R. If R is equal to 1, then it is the same value there, and then this R need not be 1. In that case, let us say if I write V in, and this is the I direction. So, we talk of the I direction, which is in this direction, and let us say we have I into R, and this is 90 degrees, and this is going to be x c into I voltage wise. So, this and this vectorially add up to V in, and this is an angle theta with this as the hypotenuse. So, the opposite side divided by this side will give you the tangent or the tan of the angle, and that is going to give you the phase angle. So, tan inverse x c by R will be theta. So, knowing the value of C here, knowing the value of omega, knowing the value of R here, you can estimate the phase angle theta which this vector is going to be displaced. Therefore, I know that the current is going to lead the voltage by this angle theta as decided by the frequency, the capacitance value and the resistance value. So, that is the importance of this space vector concept. Now, here we see one important thing. There is a voltage across this V c, and there is a voltage across this which is V r. So, we can now extend the KVL. Now, we said that the algebraic sum of the voltages in a loop should add up to 0, that is Kirchhoff's voltage law. Now, we can extend it now by saying in the steady state, if you are doing sinusoidal analysis with vectors, the vectorial sum of voltages across in a loop, across the components in a loop will add up to 0, or the voltages of all the components, the vectorial sum of the voltages of all the components should add up to the input vector, which is what is happening here. We have the input vector, this is the input vector, we have the voltage across at VR and we have the voltage across the capacitance VC. So, we have V in, we have VR and we have VC. this is 90 degrees. They are all adding up to this resultant V in, which is what Kirchhoff's voltage law would state in the normal sense, that you need to have the voltage to be 0 in a loop, vectorially also. Now, if you look at an RL circuit, an RL circuit is written like this. This is also familiar to you. We have gone through it many times. You have L, you have R, you have V in, and this is the voltage that we want to take it as a reference, and there is going to be a current I in the circuit. This has a reactance JXL. So, let us take the alpha beta coordinate system or the spatial coordinate system directly. Alpha beta, this is the spatial coordinate system. We have the reference which is V in. So, we start with V in. Now, we know that the current is going to lag. So, let us write down the current is lagging the voltage, and this is the current direction. This is the current direction. Now, I into R, which is going to be in the same direction. Okay. So, let me say that this is IR, this is going to be in the same direction. Let me put this as I into R. Now, the voltage across the inductance is XL into I, but rotated 90 degrees. Rotated from here, rotated 90 degrees in the positive, that is anti-clockwise direction. So, you have I into XL, which is rotated 90 degrees. This is IXL. So, there is an angle theta here. So, theta is equal to tan inverse XL by R, which is equal to tan inverse omega L by R. So, you get the phase angle or the phase lag of the current space vector with respect to the voltage space vector. Here also you see that the voltage across R V R, the voltage across L V L vectorially add up to equal V in. They vectorially add up to equal V in, such that the voltage across the loop is 0. Kirchhoff's voltage law is valid, and thereby upholding the principle of energy conservation. Now, this whole unit set of vectors are going to rotate with a frequency omega given by 2 pi f, which is equal to 2 pi by t, and this is a picture taken at an instant where V in projection on the temporal axis is 0. You can apply it now to an RLC circuit. You have R, L, C. So, you have RLC, V in the input source, the reference, R, this is L and C, this is going to give an impedance JXL, this is going to give an impedance minus JXC. And in the spatial coordinate system, alpha beta coordinate system. So, we have V in reference. So, you always start with V in reference because you are applying V in and you know at what point it is going to cross 0, and let us say we take that one as the reference. And depending upon the values of L and C, the current could lead or lag. So, we do not know whether it could be in phase, lead or lag. If the capacitive reactances of these two are same, then it is going to be in phase because it's R is the only impedance, or if the inductance dominates, then the current is going to lag. If the capacitance dominates, then the current is going to lead. Now, let us say for example, the capacitance dominates, which means the current is going to lead. So, now to apply the Kirchhoff's voltage law, how do the currents look like? How do the voltage using this current, how will the voltages across look like? So, we have the current, so which means the voltage across R is going to be in phase along this line, The voltage across the inductor is going to be orthogonal to this, and so also the voltage across the capacitance. So, which means they have to be orthogonal to this line. So, this is 90 degrees. Okay. So, I into R, let us say, is this vector I into R. Now, along this rotating by J, would be JXL, and along this rotating by would be the JXC, because along this minus J rotates it by minus 90 degrees, JXL rotates it by plus 90 degrees. Okay. So, along this is going to be. Now, these two being 180 degrees in opposition, the resultant of this is what is going to come across this one and fill up the gap here, and that would be XL minus XC. That would be XL minus XC. Of course, in this case, when we say XC dominates, meaning XC value is more, then we take XC minus XL. We take it as XC minus XL. So, in such a case, the XC value is dominating, and this will cancel out XL, and then that completes the vectorial sum for V. If the current were lagging, which means inductance dominates, the current would be here, and then XL would dominate XC, and it would be XL minus XC. We will look at this in detail more in the next class, and few more other circuits to understand, to consolidate the process of phasor analysis much better. Thank you.